Welcome back to Tracing the Sky. Well, I'm really excited for this episode and the next few because we're going to be diving into Copernicus. And so we'll do a mini series on Copernicus and his model of the solar system. You've probably heard of Copernicus, and he's very well known for the Copernican revolution, which is this shift towards a heliocentric model of the solar system. Now, before we get into what that is, we're going to set the stage in today's episode. We're going to look at the context in which Copernicus emerges. We'll kind of do a little recap of where we are, the significant steps that have been taken, and just where everyone's headspace is at, and kind of the core ideas that have dominated astronomy, because Copernicus is really going to upheave at least one of those principles. And we'll look at some of the questions that Copernicus is contemplating and needs to answer in order to make way for his theory of the solar system. So let's dive in together with that context setting today and look at those questions that he's answering. So where are we at in our history of astronomy? Well, we started with a really deep dive in the ancient world, looking at how things were moving. We saw the daily motion of the stars, the sun, the moon, the planets, this east to west circular motion that seemed to repeat day after day after day. But then we noticed all of these different patterns starting to emerge, different kinds of motion that were causing certain things to wander through the stars as a backdrop. And we looked at how the Greeks in particular started to ask questions about this and try and model these behaviors using geometry and math. This kind of climaxed with Ptolemy and his model of the solar system, and how he was able to add a level of precision that was not seen up until that point. We looked at what it meant to describe things mathematically and geometrically. And one thing that kind of overarched this whole story were these ideas and principles embedded in Greek thought and astronomical thought. And there were really three main things I want to draw our attention to because they'll become really important for our story as we move forward. The first is the idea of geocentricity, right? Geo meaning the earth-centered, centric-centered, right? So geocentricity is earth-centered. And this idea that the earth is at the center of all things and all of the heavenly bodies are orbiting around or rotating around the earth. And we saw that every model from the Eudoxian spheres to the Ptolemaic system had the earth at the center or slightly off center, but everything going around the earth. The next two important principles kind of summed up as one is uniform circular motion, right? So the motion is circular, i.e. perfect circles, and uniform at a constant rate, right? So each of the celestial bodies were going around circles that were moving at constant rates. Now we saw that various astronomers introduced multiple circles and each of those circles moving at constant rates, but everything had to be circular and everything had to be moving in a uniform way. If you recall, that's kind of where Ptolemy got into a little bit of trouble, where some people questioned whether his model was truly uniform motion because he had the equine point speeding up and slowing down the epicycle around the deferent. But this idea was still really embedded, and he was still striving for uniform motion, at least from the perspective of the equine. So these three pillars, as I like to think about them, geocentricity, uniform motion, and circular motion, are really embedded in every model that we see. And that's really important for Copernicus, because Copernicus is going to challenge one of those pillars. Now, leading up to Copernicus, we have a period of kind of stagnation, if you will. At least in Europe, they're going through really turbulent times after Ptolemy, right? Fall of the Roman Empire, a lot of chaos in Europe. And so it's going to be a while before they're able to start working on astronomy and making advances. Now, in the Islamic world, and like what we know now as the Middle East and Northern Africa, they had access to the Greek works, right? They had kind of inherited a lot of Greek works and traditions, and were certainly contemplating and, thinking about Ptolemy. But his basic model was still the standard for over 1,000 years, right? Though they made some improvements to the measurements and, certainly questioned some of what he had to say, a lot of his model would be still the standard for over 1,000 years. And it's when the Greek works start to get reintroduced into Europe that the Europeans start rethinking this. They get access again to the Greek works, and they're starting to revive their contemplation of it. And then we have what we know as the Renaissance, which you've probably heard, where it really starts to get going. And that's really the world into which Copernicus emerges, right? Europe is well underway to their revival of the Greek works, to thinking about these things, to examining Ptolemy and what other Greek thinkers had to say. And so Copernicus isn't coming at the beginning of that. And so he's emerging in this world that is actively thinking about these things. And so that's where we'll kind of start our story with Copernicus. So Copernicus is born in 1473 in Poland. And like I mentioned, he's born in a time where they have access to a lot of this Greek thought and are contemplating and trying to make progress in astronomy. Now, he's not satisfied with what's been done to date. He doesn't think it provides a cohesive enough system. You can't tell the order of the planets, for example, or how far they are relative away from the Earth. There's some ambiguity in particular when it comes to Mercury and Venus, and we'll cover that in the next episode. But he thinks that the models are just lacking in their cohesiveness. They do a good job, like I said, of predicting where things are going to be on a planet-by-planet basis, but they're not tied together as a cohesive system. And so this is really bugging him. And as he's looking at Greek thought, he thinks that there's a case to be made that the Earth is moving, right? What if the Earth is moving, not everything else, right? And there are a few reasons that, you might think about it this way, right? From what we did with Aristarchus as an example, that the sun is much larger than the Earth. And so there's a question of, does it make sense that everything is going around the Earth? And so Copernicus starts to think about this, and he starts to realize that a lot of things could be made much more simple if the Earth is moving in two ways. First of all, if the Earth is rotating on an axis, right? If the Earth is moving around, it explains the daily motion, right? If the Earth is moving, then, well, that could explain this east-west motion we see everything doing, right? We know that there's that daily motion, that all of the celestial bodies adhere to it. The sun, the stars, the moon, the planets, they all have this east-west motion. Well, if the Earth is turning, that would explain it. And then the second kind of motion is, well, what if the Earth is moving through space around, let's say, the sun? If the Earth is moving around the sun, well, that might explain why we have this second kind of motion, right? So if every day the Earth spins once around, and then over the course of time the Earth is also moving through this system, then that might explain why we have these two kind of motions, why we see what we see every day, but then why everything is shifting slightly over the course of time. And as he's contemplating this, he realizes that it actually simplifies a lot of other things. And so what we'll be doing in this series is looking at the model he proposes and how it simplifies things a lot and how he's able to mathematically demonstrate and explain his model and its benefits to the people. Now, before we do that, there are some big questions he has to answer, right? Because it's not like no one has contemplated this before, but there are some people who would have very strong objections to this idea that the Earth is spinning around and hurtling through space. So let's look at those objections first, because that's actually where he starts his book. He knows he's got to win some people over, and so he has to take on some of the most common objections and provide at least satisfactory answers. Otherwise, no one's going to take him seriously. So I won't cover every single objection that he deals with, but I'll cover just a couple of the major ones. The first one we can kind of bundle in as apparent motion, and there are a few different varieties of this, but the main essence is, if the Earth were actually spinning once around each day, it would have to be moving very, very fast. For the whole Earth to do a single rotation once every day, it would be moving really, really quick. And the question is, why don't we feel that? Why isn't the things flying off the Earth? Or, why don't we feel the wind in our faces from it? That's a big concern, right? Surely if the Earth were moving as quickly as it would have to be, we would notice that. And so what does Copernicus say about this? Because we have to keep one thing in mind. They don't have a lot of really advanced ideas about motion at this point in history. Physics is still very undeveloped, and it's going to be a little while before they really fully understand this. But Copernicus does have some answers and some good intuitions about this. An example he gives is if you're on a ship, right? If you're on a ship and you're sailing, and you as a person on the ship do not feel like you are moving, right? If it's a windy day, you feel the wind, but on a calmer day, you don't really feel a lot of motion, but it appears as if everything is going by you. The shore is sailing by you in the opposite direction. One modern example I'll kind of give that can help you start to think about this is, let's say you're in an airplane, as many of you probably have been. When you're in the airplane, it's moving really, really quick, but when you jump up, you don't fly to the back of the plane. Now, you might not be able to explain exactly why that is, but there are phenomena in life that you can point to where something is moving or something you are on is moving, and yet your experience of that is a little bit different. So that's a general idea or general answer he gives to the first. One of the other big objections is, surely if the Earth were now moving through space, right, through this system, let's say orbiting around the sun, the distance it would be covering is very vast, which is true. It would be traveling, let's say, from one side of the sun to the other, and that distance would be quite far. Well, wouldn't we see some observed parallax in the stars? Wouldn't the position of the stars change in a really drastic way, right? We do know that the stars shift over time, but it's not that they're changing their orientation in the sky. It's that the entire sphere of stars is rotating. What we're talking about would be something a little bit different. Well, Copernicus has an answer for that too. We know that these things are really far away, and we've already actually looked at this in our series. If the stars are really, really, really far away, then the amount that the Earth travels from one side of the sun is negligible. If these stars are so vastly far away, distances we can barely contemplate, well, the distance the Earth travels on either side wouldn't affect what we see. And this gets back to the experiment we kind of did together, right? If you remember, the way I explained parallax is to hold your finger in front of your face and close either of your eyes if you can, or cover your eye. If your finger is closer, then the observed parallax is more apparent, right? Your finger will jump more the closer it is to your eyes. The further away you bring your finger, the less it jumps. So if your finger were really, really far away, if you could extend it really, really far away from your face, you would not see any parallax at a certain distance, right? As you close each of your eyes, you wouldn't notice a difference. And so Copernicus answers it that way too. He says, well, the stars are just really, really far away. And so that's how Copernicus starts, is he starts by answering the objections, and there are a few more, but they're mostly variations on those. He answers those objections because he wants to get those out of the way so that he can really dive into his model. So in the next episode, we'll look at how he starts to present his heliocentric model, right? He is going to do something radical and break from geocentricity. He's going to put the sun at the center of the solar system, and he's going to say that the Earth is spinning around its axis every day. It's spinning. That's the cause of our daily motion, and it's going around the sun, and that is what causes all of our motion. And all of the planets are going to be doing the same thing. They're each going to be going around the sun, and they're each going to be at varying distances. So in our next episode, we'll look at how he uses this model to immediately point out how it's better than Ptolemy's model, how it's able to improve on some of the ideas, and how it simplifies and better explains certain things. And we'll start with Mercury and Venus, and showing why those present particular problems for Ptolemy and why under the Copernican system they really drastically simple. And then in future episodes we'll start to look at how he mathematically demonstrates his model. So I hope you'll join me on this journey. We're going to have a lot of fun diving into Copernicus. I'll see you next time.